series of chance talks, sadly, which today will be on Bayesian networks and information.
Thanks very much. Well, it's been great speaking here. I'm giving little tastes here and there of how to use networks and category theory to study various interesting subjects deliberately other than the theme of the QMAC group that invited me. So in other words, not quantum mechanics or quantum computation or even really computer science, but all sorts of other things to which the same techniques potentially apply. So this network here is an example of a Bayesian network that shows different factors, different variables involved in the coral bleaching crisis that we're facing. Coral reefs getting bleached partially due to global warming. So it's an example of a Bayesian network, which I'll talk about at the end here. So last time I started introducing the theme of stochastic mechanics, where we work with good old-fashioned probabilities instead of quantum amplitudes. And I think there's a lot of room for exploration there because for some reason the sophisticated people who know about category theory like to apply it nowadays to quantum mechanics, but not so much to probability theory. So there's room for exploration. So here's the kind of thing I'll be looking at. Suppose you have two finite sets. You might think of them as states, sets of states of some system. Then a stochastic map maps each element of the first set, x, to a probability distribution on the second set, y. So what that means is that for each pair of elements, one in x and one in y, we get a real number such that if you fix a particular x and look at those numbers for all points y, you get a probability distribution. So it's a generalization of a function that instead of sending a point to a single point, sends a point to a probability distribution of points. And so those numbers would be the probability of the output y given the input x. So a little bit more legalistically, what we mean is that for any point x and any point y, we have a non-negative real number such that if you fix a particular x and you sum up these numbers over all choices of y, you get 1, so that they represent a probability distribution on the set y. So this is a very basic category here, the category of finite sets and stochastic maps between them, which is good for understanding random processes, processes where what you do doesn't determine what happens, but only determines a probability distribution of what might happen. Why is it a category? Well, it's a category because you can compose stochastic maps. So a stochastic map is really a matrix of numbers, so you can compose them by doing matrix multiplication. So G composed with F will be a matrix that tells you the probability that if you start at X, that you wind up at Z, and this is the formula for matrix multiplication, but it has the meaning that you look at the probability. Sorry, these numbers are screwed up. Sorry, that should be an X there. So you take the probability that you start at X and go to some intermediate state Y using the stochastic process F times the probability that you go from that intermediate state Y to the state Z using the stochastic map G, and you sum over all intermediate states. So of course, we all know about matrix multiplication, and that's all this is, but it's good to remember that Heisenberg reinvented matrix multiplication all on his own when he was inventing quantum mechanics, where instead of probabilities, he was thinking of matrices of complex numbers, and he was trying to imagine a new description of the world where a quantum process would be described by a matrix of complex numbers, and the meaning of those matrix entries would be the amplitude that starting in some state X, you wind up in some state Y, and he invented this formula as the obvious formula for how you compose those quantum processes. And then his thesis advisor, Bourne, told him, "You've reinvented matrix multiplication. Go read a book." Which is fascinating, of course, because one thing that means is that even a very good graduate student in physics in that era wouldn't have learned matrix multiplication in the normal curriculum, whereas by now it's considered standard. So maybe there is progress in the world after all. So now we're just reusing that in the much simpler situation of probabilities. With quantum mechanics, the big question was, well, what do these amplitudes mean? But in probabilities, there still are questions what they mean, but they're less mysterious. So we get a category, which I'll call fin stock, fin for finite, because you can imagine an infinite version of this as well, and stock for stochastic maps. Stochastic is just a fancy word for random. So finite sets are objects, and stochastic maps between them are morphisms. And whoops, this is a really bad slide. There should be little wiggly arrows for stochastic maps, so that wiggliness means that it's random. Because there are also actual functions, of course, from one finite set to another that have no randomness. So that's what I'm saying here. If you give me a function from x to y, it gives you a stochastic map where each point in x gets sent to a probability distribution that's completely concentrated at one element of y. 0 everywhere except at that one point, and 1 there. So that means that you have a kind of inclusion of the usual category of finite sets and functors into the category of finite sets and stochastic maps, so a functor between them. So it's nice to be able to play back and forth between these two categories. So what can we do? Well, very basic thing we can do is look at stochastic maps from a one-element set to some other set. So, in category theory, you choose your one-element set. Don't tell anyone else what the element is, because they don't really care about that, and you just call it the one-element set. So a stochastic map from the one-element set to any other set, well, what would it be? It would assign each element of here a probability distribution on here. So there's only one element in here, so it would just be a probability distribution on x. So a probability distribution is the simplest case of a stochastic map. And very often in probability theory, we're interested in a finite set of states with a probability distribution on it. So if it weren't finite, we could call that kind of thing a measure space, or a probability measure space, more specifically. But here it's a finite set. I don't know, this is a horribly long term for such a simple thing, and it's even confusing, but I'll call this a finite probability measure space, where finite applies to the fact that the space is a finite set. There's also something called a finite measure, but that's irrelevant, okay, for what we're doing. Anyway, those things, though I need a shorter name for them, are very basic. So if you like flip a bunch of dice, you have a set of possible outcomes, you get one of these things, a finite probability measure space. So I want to think about these things, and of course in probability theory people have thought about these things for over 100 years, but I want to think about them using the tools of category theory to look at things in a new way. So we're leading up to that. So there's a category of these finite probability measure spaces. So here's a finite probability measure space, a probability distribution on x. Here's another one, so we're getting a probability distribution on y. One kind of thing you can look at is a function from x to y, which when you compose it with p, the probability distribution on x, gives you q, the probability distribution on y. Remember, functions are special cases of stochastic maps. So I can compose a function with a stochastic map, and in general I'll just get a stochastic map. So it makes sense, it parses to say that doing p and then f is equal to q. And if you figure out what that is, what it means for this triangle to commute, you see that it means sort of the only thing you might have guessed, the only sensible thing, which is that it's a function which carries one probability distribution on x over to this other one on y. So if you unravel the matrix multiplication involved in composing stochastic maps, and if you turn this function into a matrix of zeros and ones, because it's a deterministic stochastic map, work it out, and you see that the equation for the matrix multiplication boils down to this equation here, which just says the probability of an outcome y with this probability measure is equal to the sum of the probabilities of the elements of x that get sent to that outcome. So this is what you could call a deterministic way of processing random data. So for example, you might flip a bunch of coins, get a bunch of random bits. So this would be a set with some probability measure on it. And then you might do something like count the number of heads you got. That would be a deterministic map from the set of n tuples of bits to the set of natural numbers, or maybe numbers between 0 and n, to make it finite. So that's a deterministic way of processing that random variable to get a new random variable. This new random variable would be the probability distribution on the numbers from 0 to n. So the probability distribution saying the probability that you had a certain number of coins land heads up. So that's a very widely studied category. If you've ever studied Markov chains, finite Markov processes, that's what you're building upon there. And if you haven't studied it, it's still easy to understand the idea of taking some random numbers, performing a deterministic calculation on them, and getting some new random numbers. So you can compose those kind of things. Those kind of things, I forgot to say, people call them measure-preserving maps between finite probability measure spaces. You can compose them. So if I have one of them here, F, and another one here, G, I can compose them. I get this new composite function here. And because this first triangle commuted and the second one commuted, then the whole big triangle commutes. That's the way it works in category theory. So you get a category where you have this new form of, new kind of morphism and a new way of composing them. Finite probability measure spaces are objects, and measure-preserving maps between them are morphisms. So you can think of these objects as a set consisting of states with a probability for each one, and these processes here, morphisms, are not random. They're actual deterministic functions carrying one random variable to another. You could also do all sorts of other things, right? You could say, why are you making these lines be straight? Why didn't you let those be stochastic too? And the answer is, well, I just feel like studying this today, but the other thing is very interesting too. There's a reason why I'm studying these deterministic maps. There's certain properties that they have. So here's what I want to use this way of thinking to study. So there's something famous called the entropy of a probability distribution. So if I have a probability distribution on a finite set X, I can perform this obscure summation here, where I take each probability, multiply it by the logarithm of itself, add them up, stick a minus sign on just to make it more confusing, actually to make it non-negative, and that's called the entropy. And sometimes it's called the Shannon entropy, to be more specific. Sometimes it's called information. Shannon sort of reinvented this concept, especially with attention to these finite sets, but it had already been present in physics. So Boltzmann and Gibbs had defined the concept of entropy in physics, where very often the set X wouldn't be finite, but the sum becomes an integral. And they invented that concept to understand the earlier concept of entropy that people got by studying heat, thermodynamics. So now it's clear to those who've thought about it enough that all these different versions of entropy that I just mentioned are really all one and the same, and if we restrict it to the case of finite sets of outcomes, this is all you need to know. This is the formula for entropy. But that's not really all you need to know, because what you need to know is why should we care about this function here? This is a funny looking thing. So what's so great about it? Well, for starters, let me just tell you the stuff that everybody already knows. So this is a measure of how evenly spread out the probability distribution is. If it's maximized, that is, when all these probabilities are equal. So if your set has n elements, all those probabilities being 1 over n will maximize this. It will be minimized if this probability distribution is 0 everywhere except at one point. I have to tell you what 0 times the logarithm of 0 is for that to make sense, so I'll tell you it's 0. So don't question me there. I mean, if you want to take the function p log p, which is clearly defined for positive values of p, and define it for 0, you want to take the limit as p goes to 0, and you get 1. Sorry, you get 0. So, did I say 1 first? It's 0. So if your probability distribution is 0 everywhere except at one point where it's equal to 1, you get no entropy, no randomness, complete determinacy. Another way to think about it is, a more precise way to think about it ultimately, once you know what these words mean, is it's the average amount of information that you would learn if someone tells you a particular element of the set X, if beforehand all you had known was that it was randomly distributed according to this probability distribution. So you could say it's the expected amount of information that you will learn when you discover the value of this random variable. Roughly speaking, the logarithm is a way to turn, or minus the logarithm, is a way of turning probabilities into measurements of how much you learn when you find out something that has occurred that had probability p sub x of occurring. So for example, if I flip a coin, and then you start out only knowing that it has a, say you know it's a fair coin, so you start out knowing it has a 50% chance of coming up heads and 50% chance of coming up tails, then log of 1/2, or minus log of 1/2, is how much you learned when you found out whether it was heads or whether it's tails. And this px out in front here is averaging, so it's a weighted average where we weight by the probabilities. Let me show you an example of that. So here it is. So you flip a coin. So your set consists of two possibilities, heads and tails. And let's suppose that the probability distribution is maximally flat, so both events have probability 1/2, then the entropy is, given by the formula, by the sum there, works out to be the logarithm of 2. Well, people who work in entropy often like to use logarithms base 2, so they would call that 1 bit of information. But sometimes people like to use logarithm base e, the natural logarithms. So then you'd say this is logarithm 2 nats of information. But people love the word bit, so we say 1 bit of information. So each time I tell you the answer to a random coin flip, you get 1 bit of information. But suppose you were sure, suppose you knew ahead of time that this coin was grossly unfair, it's a lot heavier on one side, or maybe my way of flipping it involved holding it in the air and just setting it down so that the heads was up. So then you would know for some reason that the probability of it landing heads up was equal to 1. So in that case, when you find out the answer, yes, it landed heads up, you learn nothing at all. You short it ahead of time. And so here we get this, and you see why 0 log 0 had better be defined to be 0. So that's how it works. And then, of course, for intermediate situations, the entropy would be intermediate. So this is just standard stuff that people are supposed to tell you when they tell you about entropy so that you get some feeling for it. But none of the stuff I've said so far completely pins down the concept and proves that the formula has to be exactly what I wrote down, the usual formula. So why do we use that usual formula? So I want to use a category theoretic point of view. So instead of focusing on the entropy of a particular probability measure space, I want to focus on the change in entropy caused by a measure preserving map. I'll call that the information loss of the measure preserving map. So it's the amount of entropy that you started out with minus the amount of information that you're left with after you've applied this deterministic process to your original random data. Like, for example, instead of telling you whether 10 coins landed heads up or heads down, this, I could just tell you the number of coins that landed heads up. That would give you a random variable on this other set. That would have less information than telling you which coin landed heads up and which landed heads down. And so there's a general fact, it's a consequence of something even more general called the data processing inequality, which says that this is always greater than or equal to 0. So it means, in this case, that if you apply a deterministic process to random data, you can only lose entropy. You can only destroy information. If you've learned about the second law of thermodynamics, this should make you nervous because this sounds exactly backwards. So there's a famous law of thermodynamics that says that under some circumstances, which you are never told, the entropy always increases. Okay, so this is exactly the opposite. Okay, this is saying that if you apply a deterministic process to random data, the entropy always decreases. So it's not incompatible with the second law of thermodynamics. It applies under different situations than the second law. And you can also actually write down a kind of category theoretic way of thinking about the second law, which I definitely want to do more of in the future, study more detail in the future. But that's not what's going on here. It's sort of the opposite side of things. That's why this subject is confusing. Also because there's that minus sign in the definition of entropy. So you can easily get mixed up about what's big and what's small. But anyway, what's nice about this information loss is that it has a very simple behavior under composing two measure preserving maps.